Okay, thank you all for coming to a new virtual time series seminar. Before I introduce our speaker and guest panelists, I just want to remind everybody that we have a workshop for junior researchers. The deadline is next week. And so please, if you're a junior researcher or no one, please do submit a paper. We look forward to your submissions. It's typically a really great workshop. And so, so please remember the deadline. It's my pleasure then to introduce our speaker today, Yannick Hoga from Duisburg-Essen, and our guest panelist, Timo Dimitriadis. Yannick, the floor is yours. We look forward to learning about self-normalized inference in regression for time series.
Okay, yeah, thanks, Majid, and thanks for the invitation and giving me the opportunity to present some recent research of mine. Before I start, maybe feel free to interrupt at any time, and I'm glad to take your questions and comments. Okay. So this is joint work together with my doctoral student, Christian Schulz. And this is very classic stuff that we do here. So it's about hack inference in time series regressions. And yeah, so how to draw valid inference on regression parameters in certain types of regressions. And we'll have a look at what type of regressions we're going to look at, namely quantile and expected shortfall regressions here. So to motivate the topic, it's well known that when you run a time series regression and you have serially correlated errors, then you need to account for this when drawing inference on your regression parameters. Yeah? So, and this literature actually fills volumes of work in the literature. In the case of mean regressions, of course. And this is, econometrics 101, perhaps not, but nothing too advanced, I would say. This changes, however, when we look at quantile regressions. Then suddenly stuff is not it's no longer so standard. So if you want to do hack robust inference in quantile regressions, you basically just have two ways to go. And one way to go is to draw on results of Galvao and Yoon and do some direct estimation of the long-run variance of your quantile regression parameter estimators, and then do standard hack robust t-tests. So that's the first option. Second option would be to use the bootstrap that Gregory et al. Proposed, and that also has shown to be a valid method to account for serially correlated errors in quantile regressions. Okay, so that's the state of the art for quantile regressions. However, other types of regressions have also garnered a lot of attention recently. And one such type of regression is an expected shortfall regression. To motivate why people are so interested in expected shortfall regressions, I can show you a little plot that defines this expected shortfall. So you see a density function here with a quantile, with the tau quantile indicated here in blue. And this is defined to be the point where probability mass tau lies to the left of the quantile, 1 minus tau to the right of the quantile. And that's basically all that the quantile is telling you. So the tau quantile, for instance, wouldn't change if all the probability mass here would move all the way out to the right tail. And the tau quantile will also not change by shifting this probability mass here in this area right close to the quantile. So it's not really informative on the tail here, this quantile. This contrasts with the expected shortfall. And the expected shortfall is defined as essentially a tail mean. It's the mean of the outcome variable conditional on an exceedance of the quantile. So in this case, that would be the tail mean here, indicated by the dotted red line. And this measure is sensitive to where the probability mass here on the right lies. It changes as that mass is shifted around the support. And that makes the expected shortfall a particularly interesting measure for studying the tail behavior of any outcome variable you could come up with. And initially, the interest in the expected shortfall came from financial risk management, and there continues to be strong interest in that literature in expected shortfall regressions. However, also in the microeconometric literature, there's now lots of papers doing work on expected shortfall regressions. High-dimensional regressions have also been developed for these types of regressions. So in a nutshell, lots of interest because of this nice interpretation of the expected shortfall as a tail mean, which is informative on the tail of the outcome. However, and that's the gap in the literature we have identified, there's actually no approach for how to do valid inference in time series expected shortfall regressions, where you suspect the errors to be serially correlated. So that's, I would say, our main contribution to allow for to propose such a self-normalized inference procedure in expected shortfall regressions. Now, if you've already seen an expected shortfall regression, you may remember that expected shortfall regressions are always estimated jointly with a quantile regression for technical reasons. We'll have to do that as well. So our starting point will actually be quantile regressions. And then from quantile regressions on, we'll go to expected shortfall regressions. Another contribution we have is to add a third method to do inference in time series quantile regressions as well. And that's quite nice because in this way we can compare the self-normalized approach with the other two approaches more directly, which wouldn't be possible for expected shortfall regressions because there's no competitor to compare it to, really. Okay, so that's where we'll continue on to quantile regressions models first now, although this is not our main contribution. Okay, so but this will give us an easier start into how we approach this this inference problem here. Because with a quantile regression, you just have one regression and not a quantile regression and an expected shortfall joint type of regression. So that will make it a bit easier. Okay, so that's our main contribution, as I said, to do inference in time series expected shortfall regressions, and this inference method in time series quantile regressions is a tight product, more or less. What we can show in simulations is that this self-normalized procedure has, as it's been reported in the literature, has excellent size. But the small price to pay for this is that you observe some loss in power if you do self-normalized inference. Okay, and finally, we'll contribute by reconsidering the growth at risk application of Adrian et al., who were not able to draw valid inference for their expected shortfall regressions for US GDP growth. And that's what we can do now using our methodology. Okay, and I'll show you later on in the application here. So, as I said, we'll start with the quantile regression model because it's very simple, and then it's easy to continue on to the expected shortfall model. Okay, so the workhorse model in time series quantile regressions is this linear regression model here, where the outcome is related in a linear fashion to covariates xt plus some error term. Well, and as usual, what gives content to a regression is actually the assumption we place on the residual. So in this case here, as we're interested in quantile regressions, we assume the tau conditional quantile of epsilon t given covariates to be 0. So in standard mean regressions, it wouldn't be the tau quantile, it would be the expectation. Expectation of the error term given covariates would be 0. Classical assumption in linear mean regressions, which here is replaced because we're interested in quantiles by this type of assumption. Now, in what sense does this give content to the regression? It gives content to the regression in the sense that one can show that under this assumption here, the conditional quantile of yt given covariates is just this linear function xt prime alpha 0, which you see here. So in this sense, we can now interpret the coefficient alpha 0 as measuring the impact of the covariates on the tau quantile of the outcome. Yeah, so this makes this interpretable as a regression that tells us something about conditional quantiles of the outcome. Okay, so now since we know that alpha 0 is the coefficient of interest, it's natural to estimate it, of course. And the way it's typically estimated is by minimizing a certain loss function, a certain in-sample loss here. And of course, we can't use the squared error loss. So squared error loss would look at difference between outcome minus prediction squared. And now it's not outcome minus prediction squared. Now it's a row function of prediction minus outcome. So conceptually very similar, but the specific loss that we need to minimize here to obtain a consistent estimate of alpha 0 needs to be different, of course. Now, this loss here, this row function here is called the tick loss function, if you're familiar with it, but it also goes by several other names. But yeah, the idea is just that this is a loss to be minimized, and it's also like the squared error loss is always positive. Okay, so that's how a quantile regression is typically estimated. Now, what's the problem? What's the problem with correlation robust inference in quantile regressions? The problem you can see here. So in this Gregory paper, they show that this estimate alpha hat is asymptotically normal with variance covariance matrix of a sandwich type form. So bed matrices D, which are of this form, expectation of scalar sparsity x prime x. So that's not the difficult part. That is estimable by non-parametric methods here. So this is actually the only term that's bugging us. The density here evaluated at 0, but that can be handled, and that's pretty straightforward. Now, what makes problems in a time series context is this J matrix here, because this J matrix is the long-run variance. It's the variance of this term here, where if xt and the errors are time series, so there's serial correlation in them, gives you all the cross terms in the long run variance. And that makes it very, very hard to estimate. Now, maybe one side comment here. What's this psi function here doing in the long run variance? The psi function is the derivative of the loss that we have minimized before. And the reason this appears here, just as an aside, is because the estimator here is characterized by the rho function having a minimum. Yeah, so actually the rho function having derivative equal to 0. Yeah? So that's how the derivative of rho pops up here in this psi function. Yeah.
Yannick?
Yeah.
Can I quickly interrupt? When I looked at extreme quantiles, I often had problems estimating this density. Do you also find that that is problematic here?
Well, the point in the end will be that we don't have to estimate neither D nor J. So everything else, everything will be taken care of by adopting the self-normalized approach. So nothing here needs to be estimated. And that's, yeah, but I can imagine that this is challenging.
Okay,
yeah.
okay. And maybe one more question. I know you're not an author of the Gregory paper, but is the difficulty of getting the inference correct for quantile regression the non-differentiability of this psi function of the Hoga estimator?
Could be the case. Could be the case.
Okay.
I haven't tried, to be honest.
Yeah, okay. I thought maybe you know.
I've read the paper, of course, but I don't think they stressed it too much. So there may be other problems
Okay.
involved.
Thanks.
Okay, so yeah, there's as I said earlier, there are two valid approaches to do inference in time series quantile regressions, and one is to follow Galvao and Yoon, who propose a consistent estimator of this J matrix here. And the other approach is to do the bootstrap for inference, and that's all I'm aware of. What, of course, both of these approaches require is they require the practitioner to choose some tuning parameters, such as bandwidth choices here, block lengths in the moving block bootstrap they have. So that's yeah, all a bit involved and comes with the usual problems of how to do it properly. So self-normalization, yeah, actually obviates the need to make such tricky choices here. Okay, so how does the self-normalization work? And in doing so, and yeah, Shao is the author who pioneered this this inference approach in time series in the time series domain. What is required is to put in some more work in deriving asymptotics for your estimator, in the sense that you need to do you need to derive a functional central limit theory for the estimator. And it's functional in the sense that it depends on this parameter S here, which cuts off the sample. So this is alpha hat S is the estimator based on the first based on the S fraction of the data. So if S equals to 1, then we're back to the full sample estimator. However, for smaller s, we'll get an estimator that is just based on if s is equal to 1/2, alpha hat of s is based on the first half of the sample. And yeah, to do self-normalization, and that's what I meant by this, you need to derive this functional central limit theorem. And it's functional because the estimator now takes a parameter, just like a function. And we do so under under very light conditions, such as a smoothness condition on the distribution of epsilon t given covariates, strong mixing condition on the data, which is also quite standard in time series, and there's also some restriction on the distributional heterogeneity in the error terms and the covariates. Okay, but we'll skip that and continue on to the functional central limit theory that we derived for the quantile regression estimator, which tells us that under these regularity conditions, our subsample estimator converges to a Brownian motion WKS with variance-covariance matrix omega. So for s equal to 1 for the full sample estimate, we recover the convergence from above that alpha hat is asymptotically normal with this variance-covariance matrix. But the functional convergence can do more. And it's this functional convergence that allows us to test this linear restriction here on the quantile regression parameters that we're interested in usually in inference problems. So the testing problem here for the quantile regression is that some linear transformation of the true parameters equals some null hypothetical value under the null. Yeah? So A is a known matrix, full rank, such that we're not testing redundant linear restrictions. And so A is known, and this null hypothetical value is known. Yeah? Leading case is always testing significance of a single coefficient here. Okay, so how does self-normalization help in testing that null hypothesis? It helps because we derive the following corollary out of that theorem, namely that under the null, we get convergence of our test statistic, and the test statistic looks as follows. So tau at Tn is our test statistic, which is a Wald-type test statistic, I would say. So on the left and on the right, you measure the discrepancy between the estimate of A alpha 0, which is just the full sample estimate here, A alpha hat 1, compared with the null hypothetical value. And if that difference is somehow large, then that's evidence against the null and we want to reject it. If there are only small differences between the estimated value and the null hypothetical value, we would not be inclined to reject it. So for small values of Tn, we keep the null, and for large values, we reject it. But now, and that's different from a standard Wald statistic, this normalizer here in the middle, this meat part here in the test statistic, if you will, contains the estimates themselves. So we normalize the differences here essentially by the parameter estimator itself, and that's why it's called self-normalization, because you need these, because you use these functional estimates, these subsample estimates of the quantile regression coefficients to normalize the outer differences. And the way it works is that Shao constructed this self-normalizer so cleverly that that when you write it out, it's a one-liner really. When you write it out, the test statistic, this omega term here simply drops out of the limit. Yeah? And that's what you can see here. So the limiting distribution no longer depends on this omega matrix, which is terribly hard to estimate in some circumstances. And yeah, it's just a functional here of Brownian motion. Of course, it's not a textbook distribution. You've got to simulate the critical values, but it's not a challenge. A is known, Brownian motion, you can simulate, and that's all you need.
Yannick?
Yeah?
I have two more questions.
Yeah.
The first one is, can you get confidence intervals from that, or do you have to invert the tests?
Yeah, you can get confidence intervals. Yeah, by essentially by this duality between tests and confidence intervals. Yeah.
Do you kind of test for a bunch of alpha naught values, and then you take the confidence interval as those values which were not rejected?
Yeah, essentially.
Okay.
Yeah.
And the epsilon is probably there
Yeah.
because very small sample sizes lead to weird estimators, right?
Yeah, it's therefore for technical reasons, but yeah, if you take epsilon too small, if you take the epsilon too small, then yeah, it could become an empty sum, and the argmin of an empty sum, yeah, that's a bit weird.
And what do you usually use in practice?
10% is what people typically use. Yeah.
Okay, great. Thanks.
Okay. Yeah, so that's our test. Yeah, reject if Tn is large and larger than the 1 minus nu than the 95% quantile of this WA distribution. So that's how it would work in this sense. It works as a Wald test. The only difference is the normalizer. Okay, so that was the quantile regression part. And now we can go a little faster for the expected shortfall part here. And now you can also see that why I started with the quantile regression, because as I said earlier, an expected shortfall regression always requires you to estimate a quantile regression first. So the quantile regression reappears here in equation 2. In this joint quantile expected shortfall regression model. And then there's the actual regression of interest to us, where the expected shortfall is modeled as a function of covariates. And yeah, similarly as before, the assumption we place here on the error xi t is what gives content to the regression. And in this case, again, we assume the tauth expected shortfall of xi t given covariates to be 0. Just like in a standard mean regression again, it would be expectation of xi t given xt is 0. Okay, and now the expected shortfall, we've seen the definition before, is just a tail mean. Again, this assumption here that we place on the errors gives us that the expected shortfall of the conditional distribution of yt given covariates is xt prime beta naught, such that again beta naught becomes the coefficient of interest in an expected shortfall regression, because it measures how the covariates affect the expected shortfall of the outcome. And the estimator that we use for the expected shortfall is a two-step estimator. So as you can see, the expected shortfall here is actually the mean beyond the tauth quantile. So what our estimator does is it disregards all the observations here yt that are smaller than the tauth quantile, than the estimated tauth quantile. Yeah, this xc prime alpha hat, that's an estimate of the tauth quantile. And then, because the expected shortfall is a mean, it tells us to minimize the squared errors. Yeah, so which is like you would do in a mean regression. So, but now that mean regression is restricted to those observations that have a var exceedance, a quantile exceedance. Okay, and here you can also see why you need to estimate the quantile regression first. Yeah, you somehow need to get a handle on this conditioning event here, and that's why you need this quantile regression part also when estimating an expected shortfall regression. Okay, so from now on, things will be very similar to how to do it to the self-normalized inference and quantile regressions. First, we need to construct this estimator based on subsamples of our observations, just like before. Yeah? We need to introduce this functional estimator, which depends on the argument S. And then derive functional central limit theory also for this estimator. And it turns out that the only assumption to the quantile regression that we need to strengthen a bit is the one that restricts the distributional heterogeneity here by also including some restrictions on how heterogeneous this xi, the error in the expected shortfall regression, can be. Okay, so we'll take exactly the same steps as before. First, this functional convergence here of the expected shortfall regression estimator, which tells us again that it converges functionally to Brownian motion with variance covariance matrix omega star. So if you were to do hack-type inference, then you would have to estimate this omega star matrix consistently. And that would be quite a pain. I suppose I haven't tried it, but I would think it is because of all these matrices that appear here. And some of them also have this long-run variance form, which makes life difficult. So self-normalization is our way to go, and this obviates the need to estimate this omega star matrix here completely. You know? So again, similar linear restriction as we considered before. Linear restriction now placed on the ES regression coefficient beta 0, where the known matrix is now B. And yeah, we get the same corollary as before. Same test statistic, same testing idea. Compare the estimate of B beta 0 with the null hypothetical coefficient. Normalize by this self-normalizer. Now every occurrence of alpha hat is replaced with a beta hat. But yeah, this is basically it. Yeah, and again, reject if this test statistic is larger than the 95% quantile of WB. Yeah, and you see it's pretty pretty tuning parameter free. So the only stuff that appears, the only tuning parameter is too big a word, I think, but the only choice you've got to make is on this on this epsilon here. So that's all you need. There are no bandwidths or other stuff that practitioners have to choose. And as I said, epsilon, choosing epsilon to be 10% is really the standard in the literature. And if people do something else, that's then a bit fishy. So you've got a good initial, good initial guidance on how to choose this epsilon.
Yannick,
Yeah.
before we start the simulations, I would have two more questions.
sure.
The first one is, could you also jointly test for a parameter in beta and in alpha? So for the quantile and the expected shortfall model?
Yes, I would. I haven't done the theory, but in practice it would work. It would work the same. So for that, you would probably just have to stack the coefficients and then construct an analogous test statistic.
Okay, so you would probably need the functional central limit theorem for the joint parameters, but that's ugly but doable. Okay.
Yeah, that would
be
it.
If I understood it, you use a two-step estimator for the expected shortfall, right?
Mm-hmm.
Could you also use a joint estimator?
I think with the joint estimator, so all this functional convergence it's typically a bit difficult to derive because of verifying such nasty tightness conditions. And now here because we've got a certain convexity in the parameter here. This gets a lot easier. So you still need to do some work, but the nasty stuff you don't have to do. And since since the joint estimator has to minimize these Fissler and Siegel losses, which I don't think are convex, or there's not a convex member. The techniques that we apply here would no longer work. Yeah.
Okay. I think it's also a good idea because for the subsamples, you need something for the estimators based on the subsamples. You probably need stable estimates, and that might blow up for the joint losses. So,
yeah, computational problems would come on top of that. Yeah.
Okay, thanks.
And that's really simple to estimate. Yeah. First step is just a quantile regression. Second step is estimating a mean regression on but you throw out some observations that don't cross the quantile. Yeah.
And then probably a generalization to the marginal expected shortfall would be pretty straightforward.
Yes.
Okay.
Yeah. One can do that. Future work. Okay. Yeah, usually I'm not a big fan of presenting simulations, but here I think I'll make an exception, but I'll make it quick. There's always so much to digest here and so little to be learned from simulations usually. But here in this case, it may be instructive to look at it very quickly. So what we take here as a time series regression is a DGP from Galvao and Yoon, which has time series covariates xt here. So the little xt here is an AR1 process and the constant, and correlated errors et here, also following an AR1 process. So, and on top of this autocorrelation, there's also conditional heteroscedasticity, which Galvao and Yoon introduced by this xt prime eta here in front of the correlated errors. So classic example of a process where inference is required. And under this setup, you can show that the tau quantile of the outcome given covariates is a linear function in the covariates, similarly for the expected shortfall. And with true coefficients given by these relations here. So alpha 0 in our notation would be now delta plus, etc. And the true expected shortfall coefficient would be this. Now, what we do here is to test linear restriction here on the coefficient in alpha 0 and beta 0. And what we do is we fix in the true DGP, we fix delta 2 to be equal to 1. And for size, that's the hypothesis we test, that delta 2 equals 1. And for the expected shortfall, likewise, we test that delta 2 is equal to 1 under the null. And then we let this 1 vary. So we choose not 1, but 1.5 to have a look at the power of the procedure. So there's not going to be a table, but a picture here, because it's easier to look at. So here, that's the null hypothetical coefficient of delta 2. And if it's 1, we see that, what you see is size. So the rejection frequencies, they all should be 5% here. And what you can see is that the self-normalized approach, so that our quantile regression self-normalized approach does well in keeping size here at 5%. Also, when autocorrelation here is strong in the errors. Yeah? So rho is equal to 0.9 here. And that points to strong autocorrelation in the errors. And what happens is, all the other methods, they have size, almost of, up to, I don't know, 30 something percent here. Okay, but that's for the IID errors. But even the methods that are designed to be robust to correlation in the error terms, so the Hack method and the bootstrap, they are wildly oversized here. So that's that's what I meant. Self-normalization gives you good size. Of course, in this case, you may infer that it gives you low power, because under the alternative, so under every value except 1, we of course reject less frequently than the other methods. But that's because almost by design, these other methods have an advantage, because they already reject a lot under the null hypothesis. So they will do a better job of rejecting also under so they have it easier to also reject under the alternative. So to make this comparison a bit fairer here, we look at size-adjusted power. So we artificially choose the critical values of the other methods to let them hold size under the null. So when this delta 2 0 here is equal to 1, so we force all the methods to have 5% size under the null by adapting their critical values, and then compare power. And what we see is that this artificial power advantage from the previous slide almost disappears, but still remains noticeable. But that's something that self-normalization is known for: better size, lower power. That's this robustness efficiency trade-off that you've got to make. So the method is more robust, gives you excellent size in all sorts of different contexts. But what you have to pay, but the price you have to pay is that you get slightly less power. But I think in view of the results we see here, that's a price most practitioners will be happy to pay if you see these liberal tendencies here of the other tests.
Yannick?
Yeah?
Looking at the right panel of what we see right now, yeah, the right one, the Hack, the blue one, seems to be getting better if you increase the sample size.
Yeah.
But the bootstrap still performs poorly. But it should be consistent in theory for that setting. Do you know what's going wrong there?
Yeah, we don't know what's going wrong. The good thing is that we can be sure it's not our incapability of programming their bootstrap, because they've got an R package. So we use the R package for the simulations. And this is also something that we noticed and really did not understand too well why it doesn't improve. Yeah.
Okay.
So we can only speculate. So we speculated a bit that the moving blocks were perhaps the length of the moving blocks was perhaps not chosen ideally. Perhaps they used blocks in their automated block length selection that were too small. Considering the large autocorrelation in the errors under this setting. And of course, if you use blocks that are too small, then this doesn't capture the strong serial dependence you have in the data, and yeah, the method performs poorly. But that's our best guess, and yeah.
Okay, it's surprising, but yeah, if you have an R package, then it's a good argument.
Yeah. Okay, yeah, so for the quantile regressions, these simulations were a bit instructive because they confirmed what's already been found in other work. Was actually our main contribution here. The expected shortfall part is a bit less spectacular because you can't compare it with other methods here. So yeah, but you can still see psi is roughly 5% and power to the left and to the right of it. Yeah. But this is hard to interpret, of course, if you don't have any competitors. But in this case, it's actually an advantage, of course, because it's more novel. Okay, so let me close with a growth at risk application, and we'll start with growth at risk in one picture. So in macroeconomics, Adrian et al. Have pioneered this growth at risk approach, where they run quantile regressions of future GDP growth on national financial conditions and current GDP growth. So these covariates here are there to capture financial conditions, current financial conditions, and current economic conditions. And the question is, how do these financial and economic conditions affect future quantiles of GDP growth? And it turns out that the answer to this question is depends a lot on what quantile level you look at. So in the upper quantiles, so for positive GDP growth, you see that the conditional quantiles of large GDP gains, they actually don't vary a lot with financial conditions or GDP or economic conditions. Yeah, the upper quantiles here are pretty much flat. So there's little variation in conditional quantiles. Yeah, as in an IID series, essentially. But this picture changes when you look at the lower tails here. Then the lower quantiles of future GDP growth, they seem to vary quite a bit with financial conditions and with current economic conditions. So here you've got these wild swings seen here in the 10% quantile of the GDP growth distribution. Okay, and now what we add here are lines for the expected shortfall, which, as I mentioned previously, is more informative. So in red here, you see the expected shortfall at the 10% level of GDP growth that is predicted by the Adrian model. And in green, you see the counterpart, the left tail counterpart here of the expected shortfall, the tail of the tail mean in the negative range, and this and here you can see the similar picture that emerges almost the expected shortfall of GDP growth in the upper tail. Doesn't vary a whole lot with the covariates, but in the lower tail, there's a lot going on. Okay, so that's the story in a picture that they told. And we supplement the story now with formal statistical testing. So yeah, as I said, it's about the conditional distribution of future GDP growth, measured either by quantiles or expected shortfall in the upper and lower tails. And we simply reconsider their application and supplement it with formal hypothesis tests here. Yeah, so what we do is we estimate the parameters alpha 0 in the quantile regression here, and the beta coefficients in the expected shortfall regression here, and then do some testing on the coefficients of the Financial Conditions Index, the NFCI, National Financial Conditions Index, to see if what we saw in the picture actually holds up in a statistically significant sense, also when applying our self-normalized method. And we see this confirmed when applying here our quantile regression results, where we see that in the lower tail, the GDP growth, the future GDP growth quantiles are statistically significantly affected by national financial conditions. So we see a strong negative effect here, with a confidence interval constructed from our self-normalized approach that doesn't include the zero, so statistical significance. However, as we move to the upper quantiles, financial conditions don't matter anymore. Yeah, recall the plot. There's no variation. There was almost no variation in the conditional upper quantiles of the GDP growth distribution. So that's confirmed here in this plot as we look along the different quantile levels. Now, a similar picture emerges for the expected shortfall, which we have defined to be consistent with Adrian to be the lower tail mean here. So in the lower tails, the slope coefficient estimate of the financial conditions indicator is negative and statistically significant. So here's the one at the 10% level, but this doesn't change too much. Also for the 30% quantile level, we see quite robust results here. In contrast, if we look at the upper expected shortfall, which Adrian et al. Call the expected long rise, we see that national financial conditions don't have an effect on the expected shortfall, on the expected long rise of the GDP growth distribution. Yeah, and the coefficient estimate is almost spot on zero here, and the confidence intervals, they include the zero for all these quantile levels. So yeah, that's what Adrian et al. Could not show in their work, because yeah, they didn't have the methodology to do robust inference and expected shortfall regressions. However, with our methods, yeah, we can shed a little more. Yeah, we can supplement the analysis by formal statistical hypothesis testing. Okay, so that's it. What we have done was to propose this self-normalized approach to time series quantile and expected shortfall regressions, which have good size, lose a little bit of power, but not much, and shown how to apply these methods to an example from macroeconomics, specifically in the growth at risk literature. So yeah, thanks, and I'm happy to take questions.
Thank you so much, Yannick, for a wonderful presentation. I'm going to stop the recording, and then we can move to the Q&A.